Okay, we're live. It's August 23rd, 11:29 p.m. And this video is kind of a basic introduction to the ELO system and some of the theory behind it. For brief context of anybody that doesn't know what the ELO system is, it would be kind of weird if you've never heard of the ELO system actually, because it's widely used across a multitude of sports, chess, online games, as well as pretty much any type of game with any type of rating in it. But anyways, the ELO system assigns each player a number or rating that determines how good you are. Essentially, it tells you how strong of a player you are, and intuitively, if you win a game, that rating goes up, and if you lose a game, that rating goes down. It's pretty simple. For those of you that don't have as great of a grasp of mathematics in general, don't worry, this is a soft introduction to how the ELO system works generally, and I won't be going deep at all in mathematics, anywhere past basic probability and elementary algebra, ability to interpret graphs and that stuff, really just middle school math at most. So anyways, why am I doing this? I mean, the ELO system has been around since the 1960s. It's been over 60 years since it was developed by a Hungarian physicist, Arpad ELO, for chess. So this isn't anything new, and I'm sure that there are countless explanations online, but I've actually even looked at some of these explanations myself to see how they approached the ELO system and their theory and how they explained it. But as I've seen for myself, as well as a lot of people actually telling me that these online explanations really only give you formulas and at most derivation. They don't tell you how the theory was developed and for what purpose and how it works on a theoretically sound basis. So that's my goal for this video, to explain it in very layman's terms. So anyways, going back to the ELO system itself, and by the way, it's pronounced ELO, because he's a Hungarian born. Arpad was born in Hungary but moved to the US when he was around 10 years old. But anyways, back to the ELO system. The ELO system is designed to be sort of a self-correcting system with a self-correcting mechanism, and it theoretically only gets more accurate with the more games played. It's useful because, well, you can lay out ratings, so you can use these rating numbers to match players together to get a better, more entertaining and closer matches. It's also just generally good to have an absolute ranking system which takes into consideration all the elements of the game that could possibly be taken into consideration. It gauges players' skill by comparing how likely they are to win against another player, and it gives you points based on how statistically likely the results are. The crucial element of the ELO system is to assume a player's ability follows the bell curve pattern. So this is a rough sketch of a pretty terrible bell curve. But again, normal distribution. So this is extremely elementary statistics. I'm sure you're familiar with the bell curve. And I'm sure you also know that this midpoint in this case, the x-axis represents on the function, this will be the average. So this is the average of all the values in this range, right? So hopefully you're familiar with normal distribution in the bell curve. But anyways, I'll try to break it down a little bit. So you can imagine kind of a match as forget about chess or sports or whatever. Imagine that each player instead brings a bucket instead of whatever athletic equipment or a chessboard or whatever. Imagine that each player brings this bucket, and inside the bucket are numbers. Okay, so you play a game. Whoever draws the higher number wins the game, and whoever pulls out the lowest number out of their bucket loses. So the numbers in this analogy actually represent the player's skill or their ability. Okay, so each player has a range. They have a range of potential play. So they have a potential of playing at a range of different abilities. So sometimes you'll be playing well, you'll be popping off, right? And maybe you'll be playing at a 14. Okay, so that's very high numbers, very high skill, very high ability. Okay, so you'll tend to draw higher numbers when you're popping. Okay, but sometimes the opposite happens, where it's just a terrible day, and you're just going to be picking lower numbers in your range. You can't go below this range. For example, player A can't go below 8 because that's the absolute minimum, so that's like represented over here. You can't go below whatever bell curve represents this player's skill. But the thing is, a stronger, better player will have a bucket that generally has higher numbers in it. So they're more likely to pick out higher numbers, even if they're playing poorly compared to their standard. So compare player A to player B. Alright, one thing you notice that in general, the numbers are quite a bit lower in player B's bucket. So because player B's range is just smaller than player A's range, right? So player A is essentially the far better player. So statistically, it'll be much more likely for player A to draw out a higher number and beat out this weaker opponent. But the thing is that it's all likelihood, right? I mean, there's still overlap in the curves. So at his worst, player A will be playing at an 8. And at player B's best, it'll be playing at a 9. So there is some room for overlap. And typically this is displayed, say here, where we have a rough graph of playing strength versus rating. So this would be player B's graph. This would be player A's graph. And you can see that we assume that they're essentially identical. I mean, in general, it's not impossible for, say, a chess grandmaster to lose to an amateur player, or a professional basketball team to lose to an amateur team. It's just incredibly and practically impossibly likely, but it's still not impossible. I mean, this gets less dramatic as you get closer in range. So, for example, a table tennis player is rated, say, 1600 is more likely to beat a player rated 1800 than they are to beat a world-class table tennis player with a rating of 2000, I can't pronounce what, 800. But it's still more likely that the 1800 player wins. So looking at this graphic, these are the frequency of the numbers that are drawn from here. Right, so this is the frequency, the relative measurement. And so this would be the player's strength and rating. And again, you can compare the averages. Where the average falls in the curve, that is their current rating. So all a rating is it's the average of the distribution curve that represents the player's strength or skill, whatever you want to say. Strength in this case isn't physical strength, it's playing strength. So the ELO system is very specific in that it lays out exactly what is expected, knowing how strong the individual players play at. So if you look at the frequency of the differences between the two players' numbers, you'll get another bell curve. So what I'm saying is, if you take the rating difference between two players, right? Ignore this arrow for right now. You'll find that the way the ELO system is designed is that, okay, look, the idea here is that anything to the right of this 0 mark is more likely for you. So anything to the right of this curve that means that player is more likely to win. So the ELO system is designed so that if one player is 400 ELO rating points higher than the other, they're 10 times more likely to win. So it's all factored around this constant of 410. And it's logarithmic, right? So I mean, this is the Bell distribution. So basic statistical knowledge would dictate that another 400-point increase rating from 400 would, I mean, it's logarithmic, and I shouldn't have to explain this actually. Hopefully you understand this relation that I'm showing on screen. So essentially what that means graphically is that the area to the right of 0, so say under 400, from here onward, this space is 10 times the area to the left. So this person on the right, whose difference in rating is 400 greater, is 10 times more likely to win here. And here it's 100 times. I mean, the graph is roughly, but so looking at these observations, it would be pretty simple to derive a formula. So we will be doing a little of that. I mean, this is elementary statistics, really nothing to fear about this, about the math level here. But let me give you some context for some of the variables. So looking at this first line, RA is the rating of player A, and RB is the rating of player B. So you'll notice that this P of A wins is the probability that player A wins the match. Okay, so it doesn't have to be the probability of A winning the match. It could be the probability of B winning the match. It's essentially the same. You just have to, you can prove that mathematically that they're essentially the same. It's the same formula because B and A are commutative. It doesn't matter which player you call A or which player you call B. So we can rearrange this. We can rearrange this formula. So this will stay constant on the left side of the equation. We're always going to try to measure the probability of A winning. So I'm going to cut that off screen. So it's 10 to the power of, this is the logarithmic part. This is the logarithmic / logistic part of this graph that you can see here. This 10 that comes up here. You can loosely relate those two. So 10 to the power of, and the difference in players' rating. This is essentially the difference in players' rating. And you divide it by 400. Remember this 400 constant. So essentially if you have a factor of 400 here, you'll get a whole number. If you have 400 or negative 400 here, exactly, you'll get, I mean, these two will divide, and 10 to the power of 1 is equivalent to 10. So you'll essentially have 10 times the so you'll essentially have the probability of A winning is 10 times the probability of B winning, which checks out, right? So you can do a little plugging of numbers here. I'm just trying to make this extremely basic here, but you can do a little plugging of numbers, and then we can really rearrange this, put it in terms of A, because we don't want, we can, the probability of B winning is simply 1 minus the probability of A winning. So you can put that in terms of A, so you can finally rearrange it. So you have the full form of the equation, and this is the equation that shows you how likely a player is to be winning one game. You can see that the formula is only based on the ratings of the two players. No other factors are considered. So some basic statistics here. A probability of 1 is of course representative of 100%. You cannot lose in this situation. If the probability is 0, you cannot win, conversely. And a probability of 0.5 is winning half the games and losing half the games, so kind of like a draw. So let's say winning a game yields 1 point, losing yields 0, and a draw is a half. Then the probability can be used as an expected score that's displayed. So the expected score is you know, how well you would score against an X-rated opponent at Y rating. So okay, your expected score, it could be 1 or 0 or 1/2. Most of the time it's going to be somewhere in between, like 0.82, meaning that you're expected to win 82% of the games that you'll play against this opponent. Or 0.23, you'll win 23% of the games. Either way, you'll get an expected score value for the games between 0 and 1. So that's that's how you were expected to perform based on your rating, based on your bucket. So, but what if you perform significantly better, or just better or worse than how you were expected to perform? If a player does better than expected, the rating will increase based on how surprising or unexpected the win was. The max rating points that you can gain or lose is determined by the K value, something that's usually a constant, and it depends on the sport or what you're using the ELO system for. In chess, the maximum you can gain or lose is 32, so the K value is 32, and the formula for gaining or losing rating is obvious. It's simply the rating of a player plus the K factor multiplied by the quantity of the score minus the expected score. So you can roughly, so your new rating is calculated by your rating before the matches plus this K constant, and then multiplied by the quantity of the score, so how well you actually played. Say you played 5 games, or say you played 10 games to make the math simple. You won 3 of them, then your score would be 0.30, but that doesn't mean you necessarily lose because you lose rating because you only won 30%. It depends on your expected score. So say you won 3 out of 10 games against a chess grandmaster while only being at 1,200 rating. That's amazing. That's pretty much, that's very unexpected. So this score will be much higher than your expected score, which as a lower rated 1,000 whatever player you were, it's going to be practically 0. Your expected score against a grandmaster would be 0. So this is going to be a very high number multiplied by this K constant. So anyways, the loser essentially loses points and transfers them to the winner. And again, it's all about expectations. Expectations determine how much is gained or lost. If a player does better than expected within a certain range, they'll gain points. Worse than expected, they'll lose points. And if they play just about as expected, they won't experience much of a change in rating. This is why ELO is a self-correcting rating system that measures both short-term and long-term performance of a player. And it's argued to still be one of the most effective skill rating systems ever made. It's long-term over time. Actually, I didn't explain this, but it's long-term over time because the rating, as you play more games, the rating becomes an actual reflection of the skill of a player. And you can think of games played as experiments or tests. Over time, you will iron out any inconsistencies in your games, whether it be lucky wins or unlucky defeats. And with more games played, you'll get a better overall greater reflection of a player's ability through a number. The more games played, the more accurate, and so it's self-correcting. It's an iterative process, and I kind of define self-correcting system here because it's kind of a word I made up, but hopefully it makes sense. I didn't want to introduce the word iterative because actually that gets into computer science, and it's technically not an iterative process. But anyways, and by the way, that K factor, the K factor I talked about, 32 is more or less arbitrary. It can vary wildly. It's subject to an intense amount of variables, such as ELO tiers, winner-loss streaks, how much time has passed between the last game. So the math I displayed here is the absolute basics of the ELO system. Don't go around thinking you've mathematically mastered and fundamentally understood the entire development of rating systems online. There's a lot more to it. I just wanted to preface some interesting facts here. And speaking of interesting facts, fun fact to close out the video, the dating app Tinder actually uses an ELO system, and it's part of its algorithm and on how it rates people. Getting swiped left is essentially a loss, and you lose some ELO points, and getting swiped right is essentially a win. ELO is part of the algorithm in determining who gets matched with who. Perhaps that's not actually a fun fact, maybe a better word is depressing fact, since if Tinder actively displayed their ELO ratings on their customers or their clients or users' pages, I mean, a lot of people would be upset, particularly most men on Tinder would end up being depressed, which is why Tinder or online dating in general is just kind of dumb.